should have given you more to say about my introduction, but I also should say thank you to Blash, who swapped with me last minute. I was due to be talking right at the end of January, and I had to make a last minute change. But our new daughter is now 2 months old, which kind of explains why. Okay, so I'm going to be talking a little bit about kind of trying to kind of understand and constrain cloud sensitivity to aerosol, particularly concentrating on clean conditions, kind of why, and in particular thinking about why clean conditions are particularly important. So the background picture here was intended to be a picture of a relatively clean condition, given it's painted from kind of the early 19th century or so. Wrong. Here we go. So now, obviously, we've seen lots of pictures like this before, and being the kind of ICCP seminar, we don't need to go into too much detail about exactly what aerosol cloud interactions are. But obviously, we know the Earth is a very cloudy place. And if you look at clouds in the right way, so if you look, for example, in the near infrared, you can get information about cloud microphysics. So if we take this MODIS image here, zoom in on a little part off the coast of California, and look at cloud droplet radius in this case, we can see big changes in cloud droplet radius. And in particular, these kind of lines in cloud where ships have added aerosol to clouds, modifying the cloud droplet number concentration and the cloud droplet size. Now, this obviously then leads to a change in cloud properties, typically increasing the cloud albedo such you reflect more sunlight back into space and offset some of the warming from greenhouse gases. But as we're aware, this uncertainty is still large, and that leads to not only an uncertainty in the forcing, but an uncertainty in future climate projections. So if we look at this image here, both of these potential kind of reconstructions of the temperature have a very similar 20th century, where they can approximately match observations, but one does it with a very strong aerosol cooling and a high climate sensitivity. The other does it with a very weak aerosol cooling and a weak climate sensitivity. So as you reduce aerosol emissions going into the future and continue to increase greenhouse gas emissions, you get a very different future behavior of the climate. Now, that's thinking about kind of aerosol cloud interactions at a global mean. There's also a lot of uncertainty in the regional pattern of aerosol forcing, right? So if we have a look here at what two different models think the rate of forcing from aerosol cloud interactions is, like the spatial pattern of it, you can see that UKASM here typically puts a lot more of its forcing into stratocumulus decks, suggesting that the key thing for determining the strength of the aerosol forcing is how sensitive the clouds are to aerosol. Whereas MIROC 5 in this case is putting a lot of the forcing in regions with a large aerosol perturbation. So saying that the forcing really comes from having a large change in the amount of aerosol rather than necessarily the kind of different sensitivity of different cloud types. If we're thinking about kind of the aerosol impact on cloud albedo for low clouds, we might split it up into three separate or kind of related changes. Right? So aerosol might modify droplet number concentration, which changes cloud albedo for a constant cloud fraction and liquid water path. Likewise, you might change cloud fraction or cloud liquid water path, which again will modify the albedo of a scene of clouds. Now, if we're thinking about aerosol cloud interactions, typically most of these changes in cloud fraction and liquid water path might proceed originally through a change in droplet number concentration. So we could think about this picture a little bit more like this, which is kind of handy because we can then separate out these different arrows and they kind of relate more to different processes, particularly in the way a climate model might consider these processes. So the kind of green arrow here relating droplet number concentration to aerosol is related to aerosol activation, determining how many droplets you have. The blue arrows are then related to the radiative properties of clouds. And the red arrows here are kind of more related to cloud microphysics. Once you've changed droplet number concentration, how does that cloud respond? So these would be typically considering cloud adjustments, right? So you modify your droplet number, maybe your droplet size as well. Then you get a change in precipitation, cloud fraction, liquid water path, for example. We're not really going to concentrate on those today, although they are really interesting. We're going to think mainly about just the Toomey effect. So the aerosols modifying droplet number concentration and changing cloud albedo for a constant cloud fraction and liquid water path. So if we think about now, or have a look at different estimates of this effect, we can see there's still a very wide range in these estimates of forcing. So on the left-hand side of this plot here, you can see a couple of black blobs and some error bars. These are observation-based estimates of the RF-ACI, the rate of forcing from aerosol cloud interactions, which is also known as the Toomey effect. Right? So just this kind of impact of changing droplet number for a constant cloud fraction and liquid water path. And we can see there's a lot of variation in our observational estimates. But there's also a lot of variation in the model-based estimates as well. So these dots on the right-hand side, the vertical position, or the y-axis here is telling you what these models think the radiative forcing is, or the RF-ACI is. You can see most models suggest that it's more negative than about half a watt per meter squared. Some models suggest it's more negative than about -1 watt per meter squared, which is pretty strongly negative. But the kind of interesting thing here is that the kind of model diversity here is pretty similar to the observation-based estimate uncertainty, right? That our models are able to kind of produce this range because we don't have a strong observational constraint on what this number should be. Maybe if we had a constraint, we wouldn't have such a large diversity in our model estimates as well. Now, the model estimates are kind of edging towards the stronger end of these observation-based estimates. Maybe that's telling us something that our kind of observation-based estimates are missing something out. But ultimately, it's suggesting here, or I'd argue it's suggesting that our kind of model uncertainty here is limited by our ability to constrain this effect with observations. Now, if we have a look at the history of these observation-based constraints, what we find is that they've gradually been getting more negative. Right? So if we start with one of the first observation-based constraints, the Kvass et al. 2008 paper, that suggested that the rate of forcing from the Toomey effect, the RF-ACI, was -0.2 watts per meter squared. As we move a bit further forward, we get to 2015. Stevens et al. Suggested that it was kind of more positive than -0.5 watts per meter squared. So -0.5 being a lower estimate or a lower bound for the strength of this effect. 2017, there were a few more estimates. So some work we did suggested maybe about -0.4. Paper by McCoy suggested -0.9. Another paper in 2019, Hazekamp suggested actually maybe -0.1. And so if we follow this to its kind of natural conclusion, if we made a new estimate today, maybe we'd be expecting something about -1.5 watts per meter squared. Now, obviously, this isn't actually because the aerosol forcing has been getting stronger over that period of time. Just our kind of ability to make accurate estimates of it has changed. Now, an interesting thing to note about these different estimates is that they use different measures of aerosol. So we can kind of note some of them on here. And that has a kind of that relates to how accurately we can constrain this effect as well. So they're not different just because they're using different measures of aerosol, but it turns out that actually that does explain part of the reason that these estimates have been getting more negative. Now, ultimately, these observation-based constraints of the Toomey effect typically work in the same kind of way. They're using some kind of estimate roughly like this equation here. And there are various terms in it, some of which we know very well, some of which we know less well. Right? So the first term here, this F with a down arrow is the incoming solar flux. We'd say, well, maybe we know that fairly well. We could go and measure it. Models can estimate this. We've now got FC and alpha C. So this is the cloud fraction and the cloud albedo. And again, maybe we figure we kind of know these okay, right? We can measure these. So they get kind of a approximate tick, right? We could go and look at them with satellite to help constrain these. There's this delta log A. So A here being some measure of aerosol, and this delta log A is then the anthropogenic aerosol fraction. Now this is much harder to get. We could say, well, maybe we can get this from a climate model, perhaps. We kind of understand our aerosol sources and sinks properly. It probably shouldn't really, maybe it should be kind of a approximately tick here. And we probably don't know it as well as we know the cloud fraction. There's a 3. We know that one pretty well from maths. Um, and then there's this term d log nd d log a, which we'll refer to throughout most of this presentation as beta. This is the sensitivity of the droplet number to aerosol. So if you double aerosol, what change in droplet number do you get? Now, this is something that's much harder to get, right? We could get it from models. We could try and measure it from satellites. But it's actually turns out that this number is actually quite uncertain. And if we look at what drives the uncertainty in the Toomey effect, turns out this beta is quite important. So this figure here now is showing for the total aerosol forcing, the ERF AER, and the Toomey effect, the contributions of different terms to the uncertainty. Right, so the yellow here is the contribution of the uncertainty in the anthropogenic aerosol perturbation, and the green here is the uncertainty in that beta term. And we can see for the Toomey effect, the bottom row, that about half of the uncertainty in the Toomey effect is coming from uncertainty in beta. About half of the uncertainty is also coming from our uncertainty in the anthropogenic aerosol fraction. But both of these terms are still important when you're considering the aerosol forcing as a whole. And part of that is because despite the fact that the cloud microphysical effects or the cloud adjustments are important, changes in droplet number drive those cloud adjustments, largely at least. And so the sensitivity of droplet number to cloud albedo is still important. But why do we care about clean conditions here? Right? Well, the first answer is that the pre-industrial aerosol environment is vital for constraining the aerosol forcing. Right, that the response of cloud albedo to aerosol emissions ultimately is nonlinear. If you add a small amount of aerosol to a clean environment, you have a much larger impact on clouds than if you add a small amount of aerosol to a polluted environment. So it's important for understanding the forcing. It's also important for understanding what the pre-industrial Earth was like. Right, so we'd like to be able to study aerosol processes in clean environments. These are generally pretty rare. Right? This paper, Hamilton paper from 2014, kind of gives us an idea about where these kind of pre-industrial-like cases on Earth occur. And in general, they are pretty rare. But we'd like to know what's going on there. We'd like to be able to study what's going on in those locations. But ultimately, even moderately clean regions are very common. Right? So if we think about the kind of detection uncertainty or the kind of observational uncertainty in measuring the aerosol index, which is a way satellites characterize aerosol, we find that if you kind of look at things where it's cleaner than about 0.06, which is definitely within the kind of noise range for this measure, large amounts of the globe, it's kind of clean there more than half the time. Right, so these gray areas are here where you're below that threshold more than half. So we really need to be able to understand these clean conditions just to understand how the Earth is working today, let alone to understand what things were like in the pre-industrial. But why are these clean conditions particularly difficult, right? Surely, clean conditions are like anything else. It turns out that measuring aerosol accurately under these conditions is more challenging than it might be under very polluted conditions when you're thinking about aerosol cloud interactions. So if we look at this case here with a dust plume blowing off the Atlantic Ocean, the Sahara into the Atlantic, we can see if we compare the dust plume to the nearby ocean that there's a clear difference in aerosol. Right, the satellite can easily tell the difference between kind of high aerosol and low aerosol. But if we look at another region nearby, say down in the bottom left, which of these two regions is cleaner? Right, the satellite has a much harder job telling the difference between very clean and mostly clean. And actually, that's something we would really like to know. Right? If we're thinking about the sensitivity of clouds to aerosol, the difference between very clean and kind of clean turns out to be critically important. And we can see that if we start to look at relationships between droplet number and overall and some measure of aerosol. So this plot here now, the kind of gray regions here are showing the distribution of droplet number for a given satellite retrieved aerosol, in this case, the aerosol index, across the globe. And the thick black line here is showing the kind of mean droplet number for that given aerosol, kind of retrieved aerosol. And so what we find actually is that while there's kind of a clear increase in droplet number with aerosol at high aerosol. If we're looking in low aerosol, actually, there doesn't seem to be much of a change in droplet number at all when we're looking at this aerosol index measure. The orange dotted line there is then kind of a linear regression through all of the data, and it suggests that its beta value might be only 0.1. So that's relatively weak. If we put climate models on top of this now, oops, okay, wrong order. If we look at other satellite measures first, or other measures of aerosol, we can see a slightly increased beta, right? And this corresponds to that increasing estimate of the RFACI over time. So if we look at reanalysis sulfate here, similar to the McCoy paper from 2017, we see that there's a kind of a stronger increase in polluted cases, but some slight increase in droplet number or slight relationship between droplet number and aerosol, even in these relatively clean cases. And if we take a kind of global difference in these beta values across the globe between these two measures, we see that in general, if you measure beta with aerosol index, so this pure satellite product, you typically get a lower measure of the sensitivity than you do if you measure it with sulfate. You can also do a similar thing by using a satellite measure of CCN, and we see again that this kind of relationship looks even steeper, and our beta value here has increased further up to 0.46. Now, if we add climate models onto this, there we go. We add the climate models onto this now. We see that climate models typically are predicting a relatively strong value for beta. Right, so up here, they're actually kind of looking more like 0.5 or so. But in clean conditions, they're doing all sorts of different things. Now, what we can do is we can look just at the very polluted cases and calculate beta for cases only where the aerosol is relatively high. And so if we do that, and we consider only these kind of most polluted 50% or so of cases, we find that these beta values for these different measures of aerosol are actually very similar, right? So we have 0.62 for the aerosol index, 0.54 for the sulfate, 0.54 again for the CCM. And if we look at the global distribution, we now see that these aerosol index estimates and these sulfate estimates line up quite closely. There's a lot more uncertainty here because we have fewer data points that go into these estimates. But ultimately, it turns out that actually, if we looked only at the polluted cases, the satellite or observational estimates would all agree relatively closely, and they'd all agree quite closely with the GCMs as well. We can see that if we plot this in a slightly different way, right? So these orange dots here are now that measure of beta high, so the measure of the droplet number sensitivity to aerosol only in the polluted cases, calculated from MODIS, this kind of vertical line here, so an observation estimate. And then these orange dots are for a range of different global climate models. And what we find is that they all actually match fairly closely, right? So they all look pretty much like the observations do. But that doesn't really constrain the forcing that much, right? All of the models are reproducing the behavior of polluted conditions pretty well. But if you look at the kind of range of forcing, constraining the polluted conditions doesn't really help you. What you need to be able to do is you need to be able to constrain the clean conditions. Okay. Right, so these blue dots here, you can see if you constrain the value of beta all, so including your clean conditions as well, you get a much better constraint on the strength of the Toomey effect or the forcing from the Toomey effect. Now, the problem here is that we've just said that measuring clean conditions is quite difficult, but also that's what we need to be able to do if we're to constrain this relationship between droplet number and aerosol that's so important for our understanding of the Toomey effect. Why is that going backwards? There we go. So one question might be, well, maybe there's a lower bound for droplet number, right? We don't really know what's going on in clean conditions. Maybe droplet number doesn't ever get below some value. Okay, and in that case, no matter what your aerosol concentration is, you would expect it to flatten off. Now, there's some evidence that things could be too clean for clouds, as it were. This example here is a ship track forming in what otherwise looks like relatively clear air. This doesn't happen very often, but you do see it. And we can actually tie this to a specific ship. So we know it was formed, that it is a kind of response to the ship. So that might indicate that there's a minimum droplet number, right? If your aerosol gets too small, then you don't see droplet numbers below a certain amount. So maybe it should flatten off, right? And beta all should be smaller than beta high. Some models would kind of some models historically have done something kind of similar, suggesting there's a minimum droplet number concentration. And it's previously been shown, particularly in this paper by Hannes Kvass in 2009, that if you implement a minimum droplet number concentration, that reduces the size of your Toomey effect. You get a weaker aerosol forcing. And that comes about on this right-hand plot here because a minimum droplet number concentration typically reduces your beta. Right, and you can see why that would be the case, right? You're removing variability in droplet number to aerosol, so your kind of linear regression there will get flatter and flatter. So if there is a lower bound for droplet number concentration, that might suggest a lower bound for beta. We can actually get some idea about whether this is the case by looking to increase the sensitivity of our measure of aerosol. So if we're thinking about now an aerosol retrieval, right? If we have our satellite up here in the top left, we're essentially getting some return from the aerosol in the atmosphere and some return from the surface. And we have to try and separate those two out. Now, if there's a lot of aerosol, then that's easier to do. The signal from the surface is relatively small. But in this case, where it's clean, any uncertainty in our estimate of the surface properties becomes a big error in our estimate of the aerosol concentration. What we can do is we can look kind of at a higher sensor zenith angle. So we look further over to the edge of the swath of the satellite image, where the satellite is looking at a kind of more slanted angle through the atmosphere. Right. So at this point here, our kind of ray has spent more time in the aerosol layer, and so it gives it better sensitivity to the aerosol, particularly in clean conditions. If we look now at the value of beta as a function of satellite zenith angle, so kind of how kind of shallow the satellite is viewing through the atmosphere. Sorry, I keep pressing keyboard buttons and it's changing the slides in the wrong order. We see that as we increase the zenith angle, this value of beta increases, right? So as we get more and more sensitive to clean conditions, actually what we find is that our beta increases and we're getting a kind of a steeper and steeper relationship between droplet number and aerosol. So that would suggest that this kind of flattening off in clean conditions is not really the result of a kind of minimum droplet number, because we can actually see if we can increase our sensitivity to aerosol, we can increase the value of beta as well. Right? And so that would suggest that our kind of beta high, the value that we observe in polluted conditions, is likely then smaller than our total value of beta. That appears to be the wrong way around. Okay. So our beta high really is a lower bound for beta. Right, so our aerosol forcing that we would estimate just from looking at the polluted cases is likely then a lower bound to our total aerosol forcing. So we might then think about whether there's an upper bound to beta, right? Maybe we would say that beta shouldn't be larger than 1. So if you double the aerosol concentration, you double the number of cloud droplets. And that seems like a fair assessment, right? That you shouldn't really be able to get more droplets than you have. You shouldn't really be able to produce a larger increase in droplets than you have percentage increase in aerosol. But actually what we find is some GCMs will produce a beta that's apparently larger than 1. Right, you can see in this case here, some of them are suggesting that you kind of double your aerosol, you get a 3 times increase in the droplet number concentration. And that might seem a little bit strange, but remember in the real atmosphere, we have variable aerosol type as well. Right, so if we had a single aerosol type everywhere, then we wouldn't expect beta to be larger than 1. But if we're changing aerosol type, we modify the aerosol optical properties. And we're only measuring the aerosol optical properties as it is with a satellite. So the aerosol physical properties that involved and chemical properties involved in activation can change in a different way. So it's possible that beta could be larger than 1, although I'd have to say it seems less likely that the beta would be that large and the forcing would be that high. So obviously, if we can measure clouds in clean conditions, that's going to give us a much better estimate of the Toomey effect. But even with a better estimate of the global value, that misses kind of a lot of the story, right? We talked about how the regional pattern of aerosol forcing can be wildly different between models, even models that have a very similar global aerosol forcing. And this produces then different responses to the aerosol forcing. Right? You get different feedbacks, for example, if you're changing forcing with a different spatial pattern. So it's clearly still important to work out where these clouds are sensitive, that we don't just want to be able to constrain this value globally. We'd like to know regionally where a cloud's sensitive to aerosol, right? What is this beta value? Now, the problem with a lot of this is that we have to measure beta by looking at temporal variation in clouds and aerosols, right? So this kind of top plot here is kind of a schematic about how this might work. We look for a variation in aerosol and a variation in some cloud property, and eventually we can draw some kind of fit between these two, which gives us a value here of beta, right? If this cloud property here is droplet number, that slope then is beta. Now, this means we need to have cases where there is enough temporal variation in aerosol properties to generate a slope that we can get. If there's no temporal variation, then we can't determine kind of an accurate slope. If we make a map of this slope then across the globe, what we find, so these regions where it's red, the sensitivity or beta is typically much larger. What we find is there is still a significant variation in this value of beta across the globe. And beta apparently looks like it's much larger in the northern hemisphere. There are significant regions of the South Pacific, for example, where beta appears close to zero. And part of this is because of a lack of variability in aerosol in these locations, which means that we can't accurately use this temporal variability method for trying to understand what beta should be. So one way we can deal with this is to look at experiments on cloud instead. And we showed kind of pictures of ship tracks at the start. That's one way, at least, we can look at the sensitivity of clouds in otherwise very clean environments where there's very little in the way of an aerosol perturbation. So this here now is an image of ships off the coast of Namibia. So these little colored dots here are ships from transponder data. And this image is from Severi. It's showing a near-infrared image. So you can see these kind of lines behind ships that are the ship tracks. And what we can do is we can look at each ship at each moment in time, or each moment where we have an image, to determine whether it is modifying a cloud at that moment, and use that as a measure of whether those clouds are sensitive to aerosol or not. So we can take some examples here. These top rows, all of them have a ship at the center of it, but you can see they're not really forming an obvious track in that image. Whereas these ones at the bottom, you can see, and these images have all been rotated, so the track should appear moving vertically down at the bottom. You can see this kind of track appearing from the center of the image down towards the bottom. Now, we could identify these by hand, but obviously that's quite slow. It could take quite a long time. If we're looking at the whole fleet of kind of 70,000 ships, and we want to do it every half hour over multiple years, that's going to take a lot of time to do by hand. But luckily, we can get computers to do it for us. Right, so we can train a really pretty accurate neural net to identify these cases where ships are modifying cloud, and then use that to start to map out where these clouds are sensitive to aerosol. So the first thing you could do is look at just where you see these tracks occurring. So this here is actually a climatology of ship tracks produced in 2007. And you can see in general, there are lots of ship tracks in the Northern Hemisphere. You see lots of kind of ship modified clouds in the Northern Hemisphere. But also there's a lot of shipping there, right? That there's a lot of kind of ship transport between major ports in the Northern Hemisphere, between particularly kind of Asia and the US. And so you see lots of ship tracks there. So primarily what we're seeing here is a concentration of ships rather than where the ships are sensitive to aerosol. But what we can do instead is say, given there is a ship, what is the probability of it forming a track? So this is a slightly different question, and obviously depends on you knowing where the ships are. But if you do that, you get a different pattern here. And what we find is, while some of the regions that we saw before are still there, right? So this region off the west coast of California is still there as a region that is sensitive to aerosol. So we see lots of ship tracks there because there are A, lots of ships, and B, because the clouds are sensitive to aerosol. If we look in the southern hemisphere, we see regions such as off the coast of Peru, where again, you have clouds that are very sensitive to aerosol. And in this case here, some ships, in general, ships have about a 10% chance of forming a track. Some ships form a track basically every time they're in that region. And some regions even further south, where it looks like clouds are also very sensitive to aerosol, but that don't show up in this original map of beta that we had, right? So this region kind of down the bottom here that's kind of outlined in red, we don't see many ship tracks there. It looks like it's not really that sensitive to aerosol if we try and measure it by the kind of temporal covariation between droplet number and aerosol. But actually, if we look at ships down there, they are very good at forming ship tracks in those kind of locations, suggesting that actually those clouds really are quite sensitive to aerosol. It's just that our current ways of measuring the sensitivity of clouds to aerosol aren't really well adapted for dealing with these very clean conditions. Now, I've added in one kind of final slide here on what this means for cloud adjustments. Cloud adjustments, so changes in cloud fraction and liquid water path, are also very interesting in clean conditions, partly because we expect them to be very different, right? So if we think about changes in cloud fraction, it's been shown that cloud fraction is strongly kind of correlated to droplet number concentration, and particularly in clean cases, right? We see a very strong relationship between droplet number and cloud fraction when clouds are relatively clean. This could be related to retrieval biases, but would also suggest that if you've got a strong change in droplet number concentration under these clean conditions, you might enhance the strength of your cloud fraction response as well in these clean conditions. Liquid water path response to cloud fraction is another potentially interesting one. So this plot in the top right here shows how liquid water path changes with droplet number concentration for a specific set of cases. And what we find in the relatively clean cases with small droplet number concentrations is that we see an increase in liquid water path with increasing droplet number concentration. Now, if we weren't previously able to characterize this relationship between aerosol and droplet number in these clean conditions, we would be missing out this potential liquid water path increase under an increase in aerosol in our estimates. Liquid water path, the kind of adjustments are also interesting for a range of other reasons as well. There are a range of potential retrieval biases here too. And some studies suggest that the kind of relationship between droplet number and liquid water path might change with location and can also vary with temperature as well, which may produce then temperature-dependent aerosol forcing or equally aerosol-dependent cloud feedbacks. But I think that's probably a subject for another talk. So then, in summary, we talked a lot today, or I've talked a lot today about clean clouds. So clouds where they're existing in a relatively small aerosol, a relatively low aerosol environment, typically one that we don't characterize well with current satellite instruments. We see that models and satellites actually converge on the sensitivity of droplet number to aerosol if you only look at polluted conditions. But those polluted conditions alone are not enough to constrain the aerosol forcing. And so if we want to do that, we would require better measurements or better observations of aerosol in these very clean conditions. Okay. The global pattern, the Toomey effect, or the RFACI, still remains a bit unclear, right? We can get a better idea about what this Toomey effect is in a global mean through this kind of comparison to models. But there is good evidence that our current methods for estimating beta are not good enough in very clean conditions, that we see kind of clouds that are clearly sensitive to aerosol and sensitive to ships in regions where our estimates of beta would suggest otherwise. And this would obviously be important for marine cloud brightening, right? If you want to modify clouds, you want to go and find regions that are actually sensitive to, where clouds are actually sensitive to aerosol. And those may not be the regions where we're currently seeing changes in droplet number concentration in response to aerosol. And finally, this kind of change in beta, this change in the sensitivity of droplet number to aerosol, can also suggest that maybe our cloud adjustments might be strong as well, produce a stronger forcing as well. But this then kind of brings us a little bit into conflict with this question as to how we reproduce the 20th century if we have a very strong negative aerosol forcing or cooling. Now, as Martina said, a lot of the results that I've talked about today are in this paper that's linked at the bottom. And obviously, if you have any questions, feel free to ask them now or send me an email later. Thank you.
Thanks a lot, Ed, for this really interesting